So today we're talking about right triangle trigonometry. We're moving into 4.3. And it's basically the stuff that we've been working on with those six trig functions. And what they're really all based on is a right triangle, right? So if I have a right triangle, and we're talking about our six trig functions, like say sine of theta, cosine of theta, tangent theta, cosecant of theta, um, secant, sorry, I forgot where I was, and cotangent of theta, right? They're really based on the right triangle. Um, and the right triangle that we're dealing with is kind of laid out like this. You've got your hypotenuse, right, which is always the longest end of a triangle, right? And then we're picking some angle theta that's not our right angle, right? It could be this one or it could be this one, right? It doesn't matter which one it is as long as we label it theta. So if I have this angle as my theta, then this line right here is our hypotenuse as usual. This part of the angle would be the adjacent, right? It's attached to the angle and it is not the hypotenuse. This would be the opposite of that angle, right? So it is the opposite of theta. So wherever that theta is, or whatever angle it is we're looking for, that's how we kind of look at it. And then the lengths of each of these three sides. So the lengths of the three sides of a right triangle make up the six ratios that defined these trigonometric functions. That define the trigonometric functions. So they make up trigonometric functions. So every single one of these is made up of ratios of these three side lengths, whether it be the opposite, adjacent, or hypotenuse. Now, you might have heard the expression SOHCAHTOA. Has anyone ever heard that? I didn't realize I was writing on an old dirty whiteboard here. Has anyone heard the expression SOHCAHTOA? Okay, you have. SOHCAHTOA is SOHCAHTOA. And what they really do is they refer to those trigonometric ratios that I was talking about a minute ago, right? I'm going to go ahead and clear this board for a second, clear the whole darn thing, which means I'm going to be starting over. So we've got So if I have SOHCAHTOA, it refers to the ratios of sine, cosine, and tangent. Now, there's people who have different ways of remembering this. Ultimately, what it's saying is that sine of theta equals the opposite. Oh, that's ugly. The opposite side length over the hypotenuse, right? OH. SOH. Cosine of theta equals the adjacent side length over the hypotenuse. And that tangent of theta equals the opposite side length over adjacent. Now, knowing the phrase SOHCAHTOA is really great if you know how to spell it, but sometimes it helps to have mnemonic devices. And I heard this once. I've never forgotten it. I teach it to all my classes, but I remember it as some old hippie caught another hippie tripping on acid. I know it's not the most graceful thing, but you will remember that, right? Some old hippie caught another hippie tripping on acid. What is sine? Sine is opposite over hypotenuse. What is cosine? Caught another hippie. Cosine is adjacent over hypotenuse. Tangent is tripping on acid. Tangent equals opposite over adjacent. You'll never forget it, right? What that relates to is what we were talking about here, is when I have this right triangle. I know that's a terrible right triangle, but here we have our hypotenuse, right? The length of our hypotenuse. If this is my theta, this would be my adjacent, and this would be my opposite, right? Because it's opposite of theta. So what I'm saying is, if this is 5 and this is 3 and this is 2, right? It would never work that way. Those numbers would never work, because 4 plus 9 does not equal 5 squared. But you get the idea, right? It would say that, okay, my sine is going to be opposite, which would be 3, over my hypotenuse, which is 5, right? My cosine of theta in this case would be my adjacent, which is 2, over my hypotenuse, which is 5. Tangent of theta is going to be the opposite over the adjacent, so it would be 3 over 2. And that's what I mean by it refers to those 6 ratios, right? Now, I said 6, but I only showed you 3. But if you remember correctly, these are my original 3 trig functions, and the other 3 are just the inverses, right? So if sine of theta is opposite over hypotenuse, cosecant of theta is just hypotenuse over the opposite, right? They just flip. So in that case, it would be 5/3. Secant of theta is the inverse of cosine, so it would be hypotenuse over adjacent, which in this case would be 5/2. Cotangent would be adjacent over opposite, which is just 2/3. Now, those numbers would never actually work because of a thing called the Pythagorean theorem, where we know that the squares, like I would have, for it to be able to actually work as a right triangle, we have this thing called the Pythagorean theorem that says the square of this side plus the square of this side equals the square of our hypotenuse. But I was just making up numbers for you to kind of see how these things all fit together, right? Sometimes you're not going to be given all of the sides. But if you look at this, if you have the sides, this is really easy stuff, right? You just go through and figure out, well, which one's which. If you're not given one of the sides, say I'm given a trigonometric function, if we need to, let's change colors. Why? Because even though blue is my favorite color, I'll stick looking at it. If we're asked to find the values, the values of the 6 trigonometric functions, the values of the 6 trig functions, right? What are those? Sine, cosine, tangent, cosecant, secant, and cotangent. And you're given a triangle that looks like this. This is our right angle. And we'll say that we have, this is our theta. We have a side length of 3 and an opposite side length of 4, but we don't know what our hypotenuse is. So we have to find that hypotenuse. Anybody have any idea how we might go about finding that hypotenuse? It's like $1 million question right there, except for not, because I don't have $1 million. It would be $1 million question if I had $1 million. Melina forgot. That's fair. It's been a while since you've done any of this. Anybody else? Moises volunteered it. It is a thing called the Pythagorean theorem that I just mentioned, right? We have a squared plus b squared equals c squared. A and b are sides of the triangle. C is always our hypotenuse. So if I have 2 side lengths, right? If I know that I have 1 side length, 2 side lengths, and it's my hypotenuse that's missing, I could just go, well, I have 3 squared plus 4 squared is going to give me this hypotenuse squared, right? And then I can just take the square root and it'll give me the actual length. So 3 squared is 9 plus 4 squared, well, that's 16, which equals 25. And that gives me the hypotenuse squared. So if I just take the square root of our c, the square root of 25 is just 5. I know that this side length now is equal to 5. Does that make sense? Jasmine, did you see that? Did you get it? Do you feel it? I think a lot of people are feeling their bed more than this class this morning. So now I can find all 6 trig functions because I have all 3 side lengths. So we know that sine, SOHCAHTOA, so sine of theta equals the opposite over the hypotenuse, right? Some old hippie. So the opposite of theta is 4. The hypotenuse of theta, we just found out, is 5. Cosine, well, cosine has caught another hippie, so adjacent over hypotenuse. The adjacent one to this angle, right, is the one that's not opposite and is not the hypotenuse, right? It's the one that's connected to it, the other side of the angle, which is just 3 over 5. Our tangent of theta, well, that's tripping on acid, so that's opposite over adjacent. So we've got 4 over 3. That's only 3 of them. We've got cosecant, which is the inverse of sine, which means we could just flip them over, right? Secant, which is the inverse of cosine, so we could just flip them over. And we have cotangent, which is the inverse of tangent. So again, we just flip them over. So that's not hard, right? It's not super mathy. The most mathy thing we had to do there was we had to find that missing side length. And that is going to happen to you in the actual assignment. So I'm going to have you guys do one, and I'm only going to ask you to find sine, cosine, and tangent. Everybody needs to participate because it is how I'm taking attendance today. So I want you guys to find the values of sine of theta, cosine theta, and tangent theta. I don't need you to find all 6. Given this triangle. All right, here's our right, here is our theta. We're going to say we have a hypotenuse of 4 and a side length of 2. So we are missing one of the side lengths. You guys are going to have to figure out what that side length is. And give it a try. You could be wrong. You could be right. Exactly, but give it a try. I'm going to turn the recording back on right now, even though we missed the explanation. So we used the Pythagorean theorem. We found that other side. Once we find the other side, then we're just putting it into the ratio form, right? We found that missing length. It is the side. It's our adjacent side, right? So it doesn't even appear in sine of theta, right? Because that's just the opposite over the hypotenuse. For cosine of theta, we've got that adjacent over the hypotenuse. So we plug it in, right? We get the 2 rad 3 over 4. We reduce a fraction. We get radical 3 over 2. And then our tangent is our opposite over adjacent, right? Tripping on acid. I shouldn't even have that in the recording. Someone's going to show their parent. I'm going to get fired talking about hippies tripping on acid. So we've got 2 over 2 rad 3. When we reduce that fraction, we're left with rad 3 over 3. It doesn't matter at this point what that side length is. Once we have all of those side lengths, it's really easy to figure out what sine, cosine, and tangent are. If I asked you to do their reciprocals, right, their inverses, which are cosecant, secant, and cotangent, that would be really easy too, right? Because you just flip those over as long as you know that sine is opposite over hypotenuse. So cosecant would be hypotenuse over opposite, right? It just flipped. Moving on, we also have some special cases when it comes to right triangles. So if you're evaluating 45-degree angles, right, and you're asked to find sine, cosine, and sine, think about a 45-degree triangle, right? We're talking about right triangles. So if I have a triangle and I know it's a right triangle, right, and that one of those angles is 45 degrees, well, all of the angles of that triangle have to equal 180. We know that our right side is 90 degrees. That means our other side also has to be 45 degrees. And what that means is that our side lengths are always going to be equal. Not our hypotenuse, but our adjacent and our opposites are always going to be equal. And they have a ratio of 1, 1, radical 2. So what that tells me is if, say, this is 3, right? Say my side length here is 3, right? That means this side length is also going to be 3. And then this one is going to be 3 radical 2. Does that make some sense? If this side length was 5, this would also be 5 because these two side lengths have to be the same. And this is going to be 5 times radical 2. So that's just a little something to think about in terms of evaluating functions. So say we left it at the 1, 1 radical 2, right? Boom, boom, boom. And I asked you to find sine, cosine, and so if I wanted you to find sine of 45 degrees, right, that would be pretty easy. I could pick either one of these 45-degree angles, right? And it would still be opposite over hypotenuse, which is 1 over radical 2. And then we would have to fix that up, right? And we'd get radical 2 over 2. If I asked you to find cosine of 45 degrees, well, think about this, right? Cosine is adjacent over hypotenuse. Well, that is still just 1 over radical 2. So we can skip the math on that and know that this is just going to equal radical 2 over 2 because we already did the math on it. Last, we've got our tangent of 45 degrees. Well, tangent of 45 degrees is caught another hippie tripping on acid, O over A, right? The opposite over the adjacent. Well, that's just 1 over 1, which equals 1. So you're going to have special cases like that. Another version of a special case would be 30 degrees, evaluating at 30. And 60, right? Think about this when we're talking about triangles again, right? If I have I'm not good at drawing triangles today. Oh, but they helped me. This is my 90, right? So if I say this is a 60-degree angle, this would have to be a 30-degree angle. They're always going to be. If I have a 60-degree angle on a right triangle, my other angle's always going to be 30 because, again, they have to add up to 180 degrees to make a triangle, right? So think about this. If I have, say, in general, these all follow the same pattern. Wherever my 60-degree angle is going to be my 1. My hypotenuse is going to be a ratio of 2. And my opposite angle from that 60 is always going to be rad 3. And I try and think of this like when I think of 45s, I go, okay, whoops, sorry. We've got 1, 1, 2. It's radical 2, but it's 1, 1, 2, right? For 30 and 60, I always try and remember I've got 1, 2, rad 3. So this one, I have 1s and 2s, right? But my 2's radical. My biggest number is a radical. Here I always think 1, 2, and then my 3 is also the radical. My bigger number is the radical, and that's how I try and think about it. Think about what it looks like if I'm looking for sine of 30 degrees, right? I'm going to be going from my 30-degree angle, right? And I'm going to go opposite over hypotenuse. Well, that would be 1 over 2. If I'm looking at cosine of 30 degrees, right? Well, cosine is adjacent over hypotenuse. That's radical 3 over 2. And if I'm looking at tangent of 30 degrees, well, my tangent is going to be my opposite over my adjacent. So that is going to be 1 over radical 3. And when we rationalize that, we get rad 3 over 3. Now let's look at it for 60 degrees. And the reason I want you to see them together is that sine of 60 degrees is going to equal cosine of 30 degrees, right? Because now I'm going from here and I'm saying, okay, cosine of this angle, this 60-degree angle, is going to be opposite over adjacent. Well, that's opposite over hypotenuse. The opposite of 60 degrees is that radical 3 over the hypotenuse, which is 2. So cosine of 60 degrees is going to be the same as sine of 30, right? Because cosine of 60 now is saying adjacent over hypotenuse, and our adjacent angle line is 1, and our hypotenuse length is 2, right? Last but not least is tangent of 60 degrees. Well, our tangent of 60 degrees is on acid, right? So our opposite of 30 is our opposite of 60 is radical 3 over 1, which is just radical 3. Like radical 3 over 1 is just radical 3. So there are some identities that work with that, but I'm kind of running out of time to give them to you, so I'll give them to you in the next lesson. But keep that in mind. I will keep the homework assignment confined to these types of problems, and we will get into the identities more when I see you guys on Thursday and how those work. Okay, so you'll have a good chance to play with all of this a little bit in WebAssign. Cyan, I am going to go fix your extensions right now before I leave, but I'm going to stop this recording first.